Alright guys, hello and welcome to this video in which we will discuss the continuity and one-sided limits. Okay, so let's go ahead and get started. So first and foremost, we're going to start out with a definition here. For those of you that are watching this video and are taking my class, I went ahead and put a star on this. This is something that is going to be on the test, definitely. Okay, so first of all, we need to talk about what it is to be continuous, right? So let's give it a definition. Okay, in the past, in your algebra classes, you've probably discussed this idea of continuity, but we're going to give it a formal definition that has three requirements that have to be met, which after we talk about it, it should probably make sense to you why it needs to meet these requirements. Okay, so it says a function is continuous at C. So we're not talking about continuity over the entire interval. We're talking about continuity at a point. So it is going to be continuous at a point C if, number one, f of c is defined. So in other words, if you plug in c into the function, you get an output. Okay? The limit as you approach c of that function must exist. Okay? And number three, and this is key to making it continuous, that limit must be the same as the evaluation. Okay? So think this through. Okay? With the next example that I give you, it's going to make sense. Okay? Let's talk about discontinuity so maybe we can then really understand what it means to be continuous. Okay? So there's two types. We have what we call a removable discontinuity and a non-removable discontinuity. Removable is when you can actually make that function continuous by appropriately defining or redefining f of c. So that's what I meant earlier. So let's look at this function right here. So it looks like it's continuous, right? Except for maybe this point right here. So let's think this through. If I ask you what is the limit as x approaches c, that's definitely going to exist, right? The limit as x approaches c would be the same from the left as it is from the right. So we would say, hey, that exists. And let's call this right here, let's call that f of c. Okay, so we can say that the limit as x approaches c of f of x is equal to f of c. So it does exist, right? Now, what's the question then is, in order for this to be continuous, what is f of c equal to? Well, as you can see, f of c, at c, we have a hole. So maybe to make this example a little bit more realistic, maybe I could say like, here is a point, right? And let's call that, I don't know, let's call that 5. So then we have that f of c is equal to 5. As you can see, these two don't match. So because they're not the same, then we cannot say that this is continuous. And even further, visually, it should make sense. Take a look at this. You have a hole there, okay? So that's the type of discontinuity, okay? That is called removable, okay? It's like you just removed one little point, okay? How can we make that continuous? We can literally, if we could erase this point and throw it back in here, then it would be a continuous function in which the limit and the evaluation would be exactly the same, okay? Now, non-removable, on the other hand, is when f cannot be continuous by redefining f of c. So in other words, you can only move one point, okay? So like here, I could just move that one point and then make this thing whole, and it would just be continuous. In this case, notice how I have one completely separate graph here from this one. It's an entire interval. It's not just one point. It's completely many points, okay? So I can't just, you cannot just pick this up, the entire function, and move it up in order to make it continuous. But hopefully it is, by the way, it is obvious for you that this thing is discontinuous, okay? Now, let's talk about the limit of this. What is the limit as x approaches c of f of x? Well, as you can see, from the left-hand side, I'm approaching this value, whatever that might be. And from the right side, I'm approaching a different y value, whatever that might be. So the limit is not going to exist there. And the moment that it fails this, then it's enough for me to say like, hey, you know what? This limit doesn't exist. Okay? So hopefully the explanation of continuity was aided by the fact of you understanding what it means to actually be discontinuous. Okay, now at this point, I'm going to help improve the definition that I provided for you last time for what a limit is. But in order for me to do that, I need to introduce a little concept called one-sided limits. Well, one-sided limit is exactly what it sounds like. It comes from one side. So in a previous video, I explained to you that in order for a limit to exist, both sides have to approach the same value. Now that's kind of vague. So when I mean both sides, I mean the left and the right. So maybe this whole idea of one-sided limits will help clear that up. So first, I want you to notice the notation that I'm using. So this says the limit as x approaches c, and it has a little plus sign here. When it has a little plus sign, it means that it is a limit that is approaching from the right-hand side. Okay? Now, on the contrary, if you have a little negative sign here, then what it means is that it is from the left side. So now we're going to improve that definition earlier where it said, hey, the limits from both sides. We're going to have to say, hey, the one side, in order for a limit to exist, if the left and the right sided limits are the same, then the function is continuous at f of c also if f of c exists. Okay, so I'm no longer going to say, hey, from both sides. I'm just going to say, if the one-sided limits are the same, then the limit exists. And even further, if the limit exists and f of c happens to be the same value as that limit, then we can say that the function is continuous. Okay, let's go ahead and try an example. So, determine the continuity of the step function, or the greatest integer function. Hope you remember this. So that's a double bar with an x at 0 by using limits. Okay, so in order for us to determine continuity, there's 3 requirements. Number 1, the limit has to exist. Number 2, f of c has to exist. And number 3, the limit and f of c have to be exactly the same. So in this problem, we were interested as to what is the limit as x approaches 0, right? So I need to find the limit from the left side and the limit from the right side. Now, from the left side, let's talk about. So here is 0, right? So here's the x value 0, right here. Okay? Now, the left side of that would be on this side, right? So think about it. If you are kind of walking from the left side and approaching 0, so that means if I'm on the graph and I'm going towards 0, what I seem to be approaching is the y value of -1. Okay? On the other side, which is the right hand side, if I'm on the right side of 0 and I'm on the graph and I start walking towards 0, notice how I am approaching 0. Now, here's what happens. I could simply ask you, what is the left-sided limit? Well, the left-sided limit is -1 and the right-sided limit is 0. So those would be true answers. But now the question is, does the limit exist? And the answer to that would be no. In order for the limit to exist, both the left and the right-sided limit have to be the same. And in this case, since they're different, then the limit doesn't exist. And if the limit doesn't exist, then it's enough evidence for us to claim that the function is not continuous. Okay, so to close that idea of a limit existing, let's go ahead and give it an actual definition. Okay, so it says, let f be a function and let c and L be real numbers. The limit of f of x as x approaches c is L if and only if the left-sided limit is equal to L and the right-sided limit is equal to L. So this is the official definition you'll find in the book, but it's something that I've kind of mentioned here in the video a couple times now. In order for the limit to exist, both the left and the right-sided limit have to go towards the same value. Otherwise, the limit is said to not exist. And if the limit doesn't exist, then it cannot be continuous. But if it does exist, then you can further explore the idea of continuity. All right, so for our last example, we're going to analyze this graph. So go ahead and copy it down if you can. And I'm just going to ask you several questions about it. Okay, so first, let's go ahead and do this very first part, so part A. It says, what is the limit as x approaches 10 of f of x? Which, by the way, f of x is this graph, so I'm just going to say this is f, okay? The entire thing, okay? So the limit as x approaches 10. Now remember, in order for the limit to exist, you need to ask yourself, so I typically don't write this, but you are welcome to, what is the limit as x approaches 10 from the left? And what is the limit as x approaches 10 from the right? So let's analyze that situation. So 10, right here, here's 10. I'm going to go up to the graph. Okay, so from the left and from the right. So from the left, so here's what from the left side, I seem to be approaching the y value of 8. And from the right hand side, I seem to be approaching the y value of 8. Therefore, if the left-sided limit and the right-sided limit are the same, then we can say that the limit as x approaches 10 would actually be 8. Okay, so part 2 of part A, it says what is f of 10? Well, f of 10, just go back to regular algebra. If you plug in 10 into this function, it seems like I get 8. Now, according to the definition of continuity, therefore, since the limit as x approaches 10 of f of x is equal to 8, and f of 10 is equal to 10, then f of x is continuous at x equals 10 because it meets all the requirements. Okay? Let's try another one. Let's say, what is the limit as x approaches 5 of f of x? Okay? So remember, once again, I'm going to kind of, you don't have to write this down, but I'm going to ask myself, what is happening from the right? What is happening from the left from that function? Okay, so at 5. So here's 5, right? So at 5, if I go from the left side, that would be this side right here. So as I'm approaching from the left side towards 5, I seem to be approaching the y value of 5, so the output would be 5 from the left side. So from the left, the limit would be 5. Now from the right, so here's 5, here's the right side of 5. So it's like I'm on this part of the graph. If I approach 5 from the right hand side, it looks like I'm approaching 1 as the output. Therefore, because the right side and the left side limit are different, then we would say that the limit does not exist. Okay? And furthermore, we can just go ahead and conclude that this part of the function is not continuous. Now you could also ask, I could also ask you, what is f of 5 at this point? Well, f of 5 in this case is equal to 3. So now we can, I mean, we already knew from this part that it wasn't going to be continuous, but now definitely, like, none of this is matching up, so we can definitely say that this function is not continuous at the point x equals 5. Okay, so hopefully with this last example, I mean, we can keep trying more with the graph, but it'll be better if you just go ahead and try it on your homework. Hopefully this video helped you understand the idea of continuity and what it means to not be continuous. Remember, in order for you to prove continuity now that you're in calculus, the 3 requirements must be met and you have to mention them in your answer. Anyways, thank you so much for watching, and we'll see you next time.